Okay, today we're going to look at the goodness of fit test with the geometric distribution. So we're going to do this by an example. Now it's really similar to the binomial or the Poisson goodness of fit stuff. So if you can try and just remember your chi-square testing from that, hopefully all of this will be okay. Okay. Right, I'm hoping you can read that. I might just bring it a bit closer for you just to read it to start with. So Sarah has a large DVD collection. Every week she picks DVDs off a shelf at random until she finds one that she would like to watch. Sarah thinks that there is about a 50% chance she'll be in the mood to watch any particular DVD. Over the course of a year, she records the number of DVDs she picks off the shelf before finding one she likes to watch. The results are recorded in the frequency table below. Question A, calculate the expected frequencies if the number of DVDs considered is modelled as a geometric distribution with a probability of 0.5. Sarah wants to check if her guess that there is a 50% chance she'll watch any particular DVD is supported by the data. So we've got to formulate the null hypothesis and alternative hypothesis and then see if she is correct. Okay. Now you might remember this, year 13's talking about this because of how silly the context is that you would just pick the DVDs off without looking and then looking at them. But anyway, fun and hilarious. Right, so we need to see the expected frequencies. Now, obviously, we are assuming here that we are following a geometric distribution with a probability of 0.5. So what we need to work out is how many DVDs we'd expect for each of these ones, okay? So recall that the probability that x is equal to x is p times 1 minus p to the power of x minus 1, okay? It would be easier for you to do this like this as opposed for you to do it with your big calculator, okay? It's much easier to do it in this form. Right, so we've got, I'll just kind of rewrite the table. So we've got the number of DVDs is 1, 2, 3. Now, because technically she could pick up as many DVDs as she likes, this one, which is the top, which obviously is the most she ever picked out, but that should be infinite, okay? So that should be more than 4, more than or equal to 4. Okay, so to calculate our expecteds, well, obviously we're going to do the probability that x equals 1 times by how many DVDs she picked in total, i.e. how many weeks of the year, which is 52. And then here we're going to do the probability that x equals 2 times 52, probability that x equals 3 times 52, and then the probability that x is, am I doing greater than or equal to? Yes, greater than or equal to 4 times 52. Okay? Right, so when we then do those, hopefully I'll just put it, we'll call that our expected calculation. You don't need to write that down, I'm just writing it down so that you can see it. Okay, so for the probability that x equals 1, again, I'm just writing this all down so you can see, we're going to do 0.5 times 1 minus 0.5, which obviously is 0.5, to the power of 0. So that hopefully, obviously, is 0.5 times 52, so that should be 26. Okay. And then we're going to do the probability that x equals 2 is going to be 0.5 times 0.5 to the power of 1. So that's going to be a quarter of 52, which is going to be 13. Okay, hopefully this is very obvious. Probability that x equals 3 is going to be 0.5 times 0.5 squared, which is going to be a half, times a quarter, which is going to be an eighth. So it's going to be an eighth of 52, which is 6.5. Obviously you use your calculator, I'm just doing it in my head. And then the probability that x is greater than or equal to 4, let's write it up here so you've got it. The probability that x is greater than or equal to x is 1 minus p to the power of x minus 1. So that is 0.5 to the power of 3, which again is an eighth, and an eighth times 52 is 6.5. Now hopefully that's so obvious because now obviously when you add all of those up, you should get 52, which it does. Okay, so those are our expected frequencies. I would, depending on the number of marks, I would sort of show some calculations of how you do it. Okay, right, the next part, I think I'll go on the next bit. So now we're basically just doing the hypothesis test for B and C. Okay, so obviously we need to set up our distribution. So here's our distribution. We've got a geometric of 0.5. So our hypothesis test is our null hypothesis. Don't forget, when you're doing a goodness of fit test, if it's chi-squared, you your null hypothesis is that there is no association, i.e. the two things are independent. When you're doing it for a distribution, your null hypothesis is that that distribution is a suitable distribution. Okay, don't get those two the wrong way around, because that's important. I think lots of us lost marks on that when we did a mock once. So we're going to say that the geometric distribution is a suitable distribution, and therefore our alternative is that x being geometrically distributed is with a probability of 0.5 is not a suitable distribution. Okay, right, so here is our, I'm just going to very quickly, just so you've got it obviously, write down our table. O being the observed, expected, E being the expected, and the total. The totals are important because they help us. So we've got 33, 26, 12 was the observed, 13 was the expected, 5 was the observed, 6.5, 2 and 6.5, obviously both of those are 52. Okay, so hopefully you recall that the goodness of fit test is the sum of O minus E all squared over E. So I'm just going to work that out here. Again, we know that we don't have to do all of this written out, but it might help you just to kind of gather your workings and know what you're talking about when you're doing it. And I know some of you do this in your big calculators, and that's fine. Just be careful that you're not messing it up too badly. So that's 49 over 26. Oh, crikey, over the expected. So that is, got time to gather all your notes while I'm doing this. So that is 1/13. Then we've got 9 over 26. Then we've got, oh, did that wrong. 2 minus that. 81 over 26. There we go. Okay, and if we add all of those up, 81 over 26 plus 9 over 26 plus 1 over 13 plus 49 over 26, you should get 141 over 26. So that is 5.2307. That's what that is. Okay, blah de blah de blah. That is our test statistic. Then we are going to talk about, obviously we need to do our degrees of freedom. Now, hopefully you can remember that your degrees of freedom, if your number of cells, not including the total, take away 1, unless you are estimating this p-value. Now, this p-value has been given to us, so we are not estimating it, okay? So we can do our number of cells, which is 4, not including the total. 4 take away 1 is 3. So our degrees of freedom is 3. Then we need to look up our chi-squared value. So don't forget we're in our table, your chi-squared value. We are doing this at, I presume, a 5%. Are we doing 5%? Yeah, 5% significance level. So here we are, 5%. Our degrees of freedom is 3, so it's 7.815. Okay, now don't forget, when you're doing this hypothesis test, we're trying to, this is how well the model fits, how well our expectation is suited to our observed. Okay, so how much our observed and our expected differ. So the bigger this number, the worse it is. Okay, now this is the most extreme value we're allowing. So here is our point. Now it's at this end because that is our highest value we are allowing, which means that this value, which obviously is less, means it's less varied from what we're expecting, is there, which obviously is in the fail to reject zone. Okay, so what we can say is there is, let's say, insufficient evidence to reject H0, concluding, and then put it into context, the number of DVDs, let's put it, the number of DVDs picked off the shelf until finding a suitable, finding one she likes, can be modelled, because that's what the null hypothesis was, can be modelled with a geometric distribution where P is 0.5. Okay, and that is the goodness of fit with the geometric. Very, very similar to binomial and Poisson. It's obviously just a different distribution, okay? Just be careful that you're making sure that you have an infinite possibility, okay, so that number comes in. Use your formula to calculate them out, and hopefully it'll be okay.